Hello again. In this video, I'm going to go over the material from section 3.6, which is about derivatives as rates of change. Now, you may remember from previous videos, we talked about two interpretations of the derivative of a function evaluated at a point. One interpretation of the derivative of a function evaluated at a point is that it gives us the slope of the tangent line to the function at that point. Another interpretation of the derivative of a function at a point is that it gives us the instantaneous rate of change in the function at that point. And in this video, we're going to focus in on that second interpretation. Now, the first example we're going to look at is a case where we have an object in one-dimensional motion. Now, this could be an object that's moving up and down in a vertical direction, or it could be an object that's moving left to right horizontally. So let's say we have an object that's moving horizontally. We can describe the position of that object with a number line that is oriented in the horizontal direction. We can also describe the position of that object on the number line with a position function. Now, you may remember we've talked about position functions before. S stands for the position of the object on the number line, and it depends on time, so it's a function of time. Okay, so let's say we take two time periods, or two times, right? When t is equal to a, and then t is equal to this time that's a little bit larger than a, which we're going to call a plus delta t. Now, delta stands for change in, so this means a plus a change in time. In other words, a plus a little bit more time. Okay, so suppose the object is located at this point when t is equal to a, at time a. And then at time a plus delta t, it's located at this position on the number line. If you take the difference, you take its position at this point and subtract its position at this point, that's known as the displacement of the object. In other words, f evaluated at a plus delta t minus f evaluated at a, that gives us this displacement of the object, which we denote with delta s. Delta stands for change in, so that's a change in position. Okay, that's known as the displacement of the object during this time period. Now, if we take delta s and we divide it by the change in time, right, we take the displacement of the object over the time period, that gives us the average velocity of the object over that time period. In fact, we can interpret that graphically. Suppose this is the graph of the position function, and we want to find the average velocity of the object between this time a and this other time a plus delta t. Now, you may remember the average velocity of the object between this time and this time is simply the slope of the secant line between those 2 points on the position function. And of course, the slope of the line between these 2 points is simply the rise of the line over the run. Now, you can see the rise of the line would be the distance between these two y values. In other words, f evaluated at a plus delta t minus f evaluated at a, which is the displacement of the object during this time period. So that's just delta s. Okay, so the rise is delta s, and you can see the run is delta t. That's the change in time down here, which is the run. So when you take rise over run, you're getting delta s divided by delta t, which is the average velocity of the object between these 2 points. In other words, the slope of the secant line between these 2 points is also the average velocity of the object between these 2 time periods. Okay, let's turn our focus towards finding the instantaneous velocity of the object at a moment in time. So let's say we wanted to find the instantaneous velocity of the object right at this time t is equal to a. So at this point P. Well, the instantaneous velocity of the object at this point A is simply the slope of this tangent line to the function at this point when t is equal to a. So how do we find the slope of this tangent line? Well, you may remember the way we find the slope of this tangent line is we look at the slopes of the secant lines between the point P and Q, and we let delta t head towards 0, and as delta t is heading towards 0, we look at the slopes of the secant lines and we see what they're approaching. And whatever they approach is the slope of the tangent line at this point t is equal to a. In other words, it's a limit. It's the limit of delta s over delta t, because that's the slope of the secant line, as delta t heads towards 0. And that's going to give us the instantaneous velocity of the object right when t is equal to a. In other words, v stands for the instantaneous velocity. So v evaluated at a. And you can see this. As delta t is heading towards 0, you can see that the secant lines are beginning to approach the tangent line. Right? In fact, the slopes of the secant lines, of these secant lines, are approaching the slope of that tangent line. And of course, you can write this limit, delta s is the displacement, right, which is equal to this. So you could also write it like that. And this is actually the definition of the derivative of the function. So this is also the derivative evaluated at a, the derivative of the function evaluated at a. So there's a couple of things going on here that, just to summarize it. The instantaneous velocity of the object when t is equal to a is simply the slope of this tangent line right when t is equal to a, which happens to be the derivative of the position function evaluated at a. And you remember an interpretation of that derivative evaluated at a is the instantaneous rate of change in the function at a. But this is a position function. So when someone gives us the instantaneous rate of change in the position function, they're actually giving us the velocity, instantaneous velocity of the object right at that point A. So they're all three the same thing. Okay, the instantaneous velocity at A is equal to the slope of the tangent line at A, which is equal to the derivative at A, which is the instantaneous rate of change in the function at A. They're all the same thing. Okay, so let's look at this first example. So in this example, we have a police station that is located on an east-west freeway. At noon, which is t equal to 0, a patrol car leaves the station heading east. The position of the car, s equal to a function of time, right? That's the position function as a function of time, gives the location of the car in miles. East is when the position is greater than 0, or west when the position is less than 0, of the station t hours after noon. Okay, and so for the part A, we're supposed to describe the location of the patrol car during the first 3.5 hours of the trip. Okay, so this is the graph of the position function. You can see down here, this is the time axis, and this is the position of the object, the patrol car. And so the first part here, part A, we're supposed to describe the location of the patrol car during the first 3.5 hours of the trip. Okay, so let's look at this. it looks like for the first hour and a half, the object at time 0 is at position 0. And then for the first hour and a half, you can see that its position is getting bigger and bigger and heading towards 80. So it's heading east initially. It starts off at 0, which is where the police station is, and then it heads towards a position of 80 for the first hour and a half. So it's heading east the first hour and a half. Now look what's happening here between 1.5 and 2 hours. It looks like its position is staying at 80. So it's not moving. It's staying at the same position for this half hour. Okay, and then it appears that from 2 to 3 hours, or 2 to 3.5 hours, the object begins to move west because its position is now getting smaller, 70, 60, 50, and then eventually it gets back to 0, so it went back to the police station. And then after that, it looks like it actually continues to head west on the other side of the police station. So it's at -10 and then -20. So this diagram may help. So here's the police car traveling east until it reaches a position of 80. Now remember, this is one-dimensional motion. So this car is only moving in the horizontal direction. Okay, so initially it starts off heading east until it reaches the 80 mark on the number line. And then it stays at the 80 mark for about a half hour. And then it begins to start heading towards the west until it goes back to position 0 on the number line, which is the police station. And then it begins traveling west, and that's why its position is now negative. So it's -10 and then -20 on the number line because it's heading west of the station. Okay, so let's look at part B. Calculate the displacement and average velocity of the car between 2 p.m. and 3:30 p.m. In other words, when t is between 2 and 3.5. Okay, so let's find its displacement first. So where is it at when t is equal to 2? Okay, so let's see. When t is equal to 2, it's at the 80 mark on the number line. 80 mile mark on the number line. Okay, and then at 3:30, which is t equal 3.5, it is at the -20 mark on the number line. Okay, so let's find its displacement. So the position function evaluated at 3.5 would be -20. By the way, you always do final position minus initial position to get displacement. Okay, so its final position would be where the object is located at 3.5 when t is equal to 3.5. That's -20. Okay, so that's its final position. So it's at -20 on the number line, right? Minus its initial position, which is when t is equal to 2. And when t is equal to 2, it's at the 80 mark on the number line, positive 80 mark. So its final position minus its initial position. So its displacement is -100. And that makes sense because it started at the 80 mark on the number line, and then it lost 100, and that's why it's at negative 20 on the number line. Okay, so that's the displacement of the object during this time period. Now, let's find the average velocity. Now, remember, average velocity is simply the displacement divided by the change in time. And of course, the change in time here is 1.5 hours. So I'm just going to divide the displacement by 1.5. And so you can see it's negative 66.666 miles per hour. So what does the negative mean? Because we have a negative sign, right? What does the negative sign indicate? Well, velocity can be positive and negative. Average velocity or instantaneous velocity. They can be both positive and negative. And that just indicates the direction. This is an object that's moving in one dimension. It's a one-dimensional motion. Positive means that it's moving towards the positive on the number line, and negative means it's moving towards the negative on the number line. So this, and that's sufficient. For one-dimensional motion, you just need to tell me whether it's moving in the positive direction on the number line or the negative direction on the number line, because it is one-dimensional motion. So this indicates that the object is moving in the negative direction on the number line, which it is. Because it starts off at 80 and then it moves towards negative 20. Okay, so it's heading towards the negative direction as it does that. In fact, it's right, okay, so right here it's at 80 and then it moves towards negative 20. As it's doing that, it's moving in the negative direction. And that's why the average velocity is a negative instead of a positive. Okay, part C. At what time is the instantaneous velocity greatest as the car travels east? Now remember, instantaneous velocity is the slope of the tangent line to the position function at any given point. And so what they're really asking us to do here is to find when the slope of the tangent line is greatest as the car travels east. Well, first of all, the car is traveling east only in this part. Once it heads this way, it's beginning to travel westward. So between here and here, right, the first hour and a half, we want to try to figure out when the slope of the tangent line would be greatest. So imagine drawing tangent lines here. The slope of the tangent line at the points in here all appear to be about the same. The slopes are all about like this. And then as you get to this point, the slopes of the tangent lines begin to level off and head towards zero. So I think the greatest is somewhere in here. It's hard to tell, but it's not down here because the slope of the tangent line down here is flatter. And then as you move into here, it gets steeper. And then at some point, it begins to level off again and head towards zero up here. So it's somewhere in here. It's very hard to tell. I would say somewhere between 0.5 and 1. And you can see that that is the correct answer. It's somewhere between t equal 0.5 and t equals 1, which is 12:30 and 1 p.m. Okay, so that's how you handle something like this. If you want to find instantaneous velocity and you're given the graph of the position function, not the graph, the graph in terms of time versus position, okay, then you can find it by looking at the slope of the tangent lines. Remember, the slope of the tangent lines give you the instantaneous velocity. Okay, and so that's how you can answer part C. Okay, so I hope you found this video helpful. Thank you for watching. Bye-bye.